received Eminent Engineer from Association of Consulting Civil Engineers, ACCE India. He has received award of Academic Excellence at IIT Madras and Outstanding Concrete Engineer Award from Ultratech and Gold Medal in PhD at Jain University. His professional affiliations are Fellow Association of Consulting Engineers India, Member of Institute of Engineers, Member of Indian Concrete Journal, Member of American Society of Civil Engineers, ASCE, and Member of Instruct India. His experiences are professional experiences. He has total 42 years in the field of civil engineering. He has experienced in Gammon India, Raheja Development Corporation. From 1999 to 1991 till date, he has established INSICON AG, an innovative civil engineering conclave. He has completed more than 350 plus projects. His academic experiences are he has published 250 plus articles and papers in national, international journals and construction industry related publications. Contributed contents for Karnataka Civil Engineers Handbook. Delivered several keynote addresses as invited speaker in international and national and international conferences, including Singapore, Tokyo, etc. He has guided postgraduate students, guided 12 graduate students in their internship programs in the field of sustainability, delivered several talks in technical institutions related to energy performance of buildings as a part of engineering curriculum. He has authored 18 activity-based books for primary and secondary school curriculum, initiated several student mentoring programs as a part of ACCE, published Build Constructions, a construction-related technical magazine, which won Best Construction Industry Magazine in India award within its first year. In the sustainability related, he sir has experience of having talks, presentations in national, international conferences on high performance buildings, energy performance of buildings, eco-friendly buildings, impact of built environment, smart cities, etc. Currently involved with the two sustainable projects in recognized by UNDP as most sustainable projects sites in India. Part of doctoral program, he has developed a new sustainability algorithm ASPSDI, helping in involving global warming mitigation strategies. He has adopted a village called Elavatti in northern part of Karnataka, India, where efforts in establishing a community campus and a school for village students on sustainable grounds. Work is in progress as on date. Sustainability auditing and buildings and infrastructure projects in reducing carbon footprint. Thank you for accepting our invitations and being a resource person for this FDP. Thank you, sir. Over to you, sir.
Thank you. Thank you so much. Just let me know if the screen is visible, okay?
Yes, sir.
Full screen is visible?
Yes, sir. Full screen.
Okay, so can I start?
Yes, sir.
Yeah. Good evening, one and all. I hope I am audible and clear.
Yes, sir. Perfectly fine.
Okay. Yeah. Good evening, one and all. And thank you for giving me this opportunity to share some of my views on today's very important topic, guidelines to sustainable construction or approach to sustainable construction. I thought more than guidelines, approach to sustainable construction would be more appropriate, because guidelines to sustainable construction means it is like a darshini. You just give tips and then there it ends the matter. And I'm sure that we are not going to discuss today. We are going to discuss really the technology behind sustainability. And I presume this being a faculty development program, and all of them have the basic knowledge of sustainability is. But however, very broadly, I will touch upon, and briefly, I'll touch upon several issues of important definitions and other things. And if you have kindly any doubt or anything, please raise your hand, and then or stop me or call me anything, I think you can unmute yourself and then just so that the entire process can be more interactive. So I think with, and then special thanks to Dr. Anuradha, who has been instrumental in bringing me this. And thank you, Dr. Anuradha. Thank you very much. So let us begin today's talk. Now, let me just briefly tell you about today's talk. If you are expecting what materials to be used into construction, what are the things, what different types, what mechanisms, and I think that is not I'm going to present. There, everybody speaks about it, and then I would like to know, because you people being the faculty of the engineering college, and as a higher education demands, I think one should have the core in-depth knowledge of what sustainability is, then all other things can actually follow. So I would like to touch upon those core issues, the basic principles of sustainability, which probably to some of you may look extremely technical, but that is how it is. Sustainability is just not some theory and then some points. It is going to be extremely technical. So I have tried to present you several case studies through which you will be able to understand, and probably you will also be able to incorporate these things as projects to your graduate or postgraduate students. So to begin with, we have seen unprecedented events of our times, the rapidity with which greenhouse gas emission is happening, the rapidity with which ocean acidification is happening, that has never happened in the last 30 crores of years. Then warming of ocean, even at the depth of 700 meters below, rapidly changing seasons. We are all changing seasons. And then urbanization, rural migration, melting of glaciers, polar amplifications, permafrost, all these actually which are attributed because of the human actions, what we call it as anthropogenic, and the warming of the earth, and then consequent climate change, increased carbon dioxide concentration in the atmosphere are the primary factors for all these unprecedented events what we are seeing. Now, we all know recently also we have overtaken China in terms of population, and this is last year's approximate extrapolation of the population. The world population is crossing 8 billions very shortly. 1.4 billion in China, 1.4 billion in India, 1.4 billion in Africa, and the rest of the countries the pictorial view what you see here, it will give you the indication of the bubble chart very clearly shows the indication of the population and the trend in which it is growing. So now there is also, and when we talk about rural migration, there is quickly let us dwell upon what exactly is urban cycle also. Now, there is an urbanization which is followed by industrialization, because urbanization calls for industrialization, industrialization calls for infrastructure development, then the environmental impact come into the picture, because the environmental impact follows greenhouse gas emissions, global warming, man-made disasters, and these all actually in turn related and then completely associated with migration, rural migration, environmental refugees, what we call. There is a slight difference between what is called as environmental refugees and migration. The migration generally refers to that category or that set of people who actually come in search of better lifestyle, better education for the children, better education, better family, better lifestyle, etc. So they shift from rural migration to a place slightly better than the rural area where they were exposed. And whereas environmental refugees are those people who, out of natural calamities, let us say in one of those rural areas where it is hit by floods, and then they've lost everything. These are the people who just look for safer place. and when they come and then they settle outside the outskirts of to tier 2 cities, tier 3 cities, they are not actually really looking for a better lifestyle or something like that, but they are just looking for a safer place. So these are actually called as the environmental refugees. So this actually urban cycle is immaterial, and then it keeps on inevitable, and it keeps on growing. Now, what are the major challenges due to climate change in future? Now, we are all in future means that is not actually, that is what actually is happening. So by virtue of this climate change, what we are seeing now, there is two extremes. We have two, either it is too hot or too cold or too windy or too rainy, etc. Now, peak electricity demand will increase, and then due to warmer and more frequent hot days, maximum capacity of current transmission systems will come into the picture. Extreme and unpredictable weather conditions will come into the picture. Potential water shortages will happen, and this potential water shortage will also lead to the uncertainty of our hydroelectric plants working, its efficiency, uncertainty over the water supplies for cooling power plants, etc. And then the danger for the natural calamities, including the danger of floods, etc. And we all know the recent flood in Pakistan, which so many people were killed. And then the earthquake in Turkey, what we are seeing, more than 50,000 people have died. So these are all actually due to extreme major changes that are happening. And these are the effects which we are already seeing. They are not future. And that's why I would like to call it like the future is now. It is not the future which we are going to face 50 years later, but the future is now. Now, in effect, this entire climate change and then global warming associated, carbon dioxide, ocean acidification takes place. The air, because of the global the greenhouse gas emission into the atmosphere, carbon dioxide keeps on increasing. The more of carbon dioxide coming in touch with H2O forms carbonic acid, acidification takes place. Then there is habitat fragmentation because of the infrastructure development. Then there are forest fires, and then deforestation, which we have seen in the recent, soil erosion, water depletion. These, and then there are several adverse impacts which are taking place. Now, let us come to the real definition of sustainability versus sustainable development. How do we actually define sustainability? Sustainability in which the components of ecosystem and their functions are maintained for the present and then future generations. So this is as per the National Building Code 2016, Part 11. Now, whereas sustainable development as per the World Commission is that which meets the needs of the current generations without compromising the ability of the future generations to meet their own needs. So these are the important definitions, what actually is the development, sustainable development and sustainability. So sustainable development becomes more and more calls for strategic approaches as engineers, and then probably it is the individual duty of every individual to be a part, to participate in saving our planet. Now, what is sustainable construction? As of now, there are several definitions to explain what exactly is sustainable construction. Sustainable construction, these I have just randomly picked up these two important definitions which are more accepted. So one definition is sustainable construction is the creation and responsible management of healthy built environment based on the resource efficiency and ecological principles. The other definition says a holistic process aiming to restore and maintain harmony between the natural and built environments and create settlements that affirm human dignity, encourage economic activity. So basically, essentially, if you quintessentially both these definitions can be put together, and then we can actually draw the means of sustainable construction. So sustainable construction itself, is a very vast subject, and we need to understand that. And before we actually start dwelling into it, sustainable construction cannot be just a simple vertical, one of the verticals where we can separate it out with respect to the other verticals of a society. Sustainable development has to be firmly founded upon three fundamental pillars of economy, socio-cultural, economic, and the environmental pillars. These are the three fundamental pillars which actually, in a socio-economical, cultural environment, they are not only, they're not just three different verticals or four different verticals, but they are actually completely interconnected. So whenever a building comes into the picture, or whenever a building is constructed, whenever an infrastructure project is developed, it doesn't just stand there as a separate entity, but it will have its own impact on the surrounding, and in the surrounding area, the surrounding environment will get affected. The inhabitat in the surrounding areas, people will be living there, will get affected. So the economic process will get affected. So that is why these founding pillars of sustainability, all of them are actually completely integrated, and there is absolute necessity to take all these things into consideration. Now, why we are talking about more of construction industry? Why more focused on construction industry, or particularly, in particular, it is infrastructure, industrial, and domestic buildings, so to say. Now, if you take the total global energy consumption scenario, or even the nation-wise, let us say in India, if you take the distribution, what you see here is actually, if you just say leave out the agricultural and other areas, if you just add up domestic, commercial, and industrial infrastructure, and then building, etc., real estate, in terms of real estate, commercial, domestic, and then now we have got mixed use, etc. So that almost forms about 73% of the entire Indian energy consumption. So natural resources are directly proportional. What we use the natural resources to produce this kind of energy is amazing, actually. See, by 2050, they say that we will almost consume about 3 times. In about 100 years, we will be requiring one more planet, Earth, to exist, to survive. So that is why now there's so much of hectic parlance is being given. Now, let me talk about SDGs, Sustainability Development Goals. Am I audible?
Yes, sir. Yes,
Yeah,
sir.
okay. So everything is clear.
Yes, yes.
Yes, sir.
All right, okay. Now let us come to sustainability development goals. Now these sustainability development goals actually were adopted by in COP21, that is Conference of Parties 21, which was held in Paris. Now this is happening every year now. Recently concluded Glasgow was COP27, and that is Conference of Parties, and wherein in this the COP21 is considered as one of the most important conference of parties, where actually they identified 17 sustainability development goals, and then the focus was given to end poverty, protect and planet, and ensure that all people will have peace and prosperity by 2030. And to be very honest with you, I represented India in one of the United Nations subcommittees since last 6 years, but we are actually quite far from it, because it is extremely difficult to meet this. But happy to note that India is on a much better place than many other countries. And our Prime Minister, Indian Prime Minister, Shri Narendra Modi, played an extremely important role in COP21, making the others realize, and then other developed countries like including USA, Germany, Japan, and all those countries to commit to them, and then told them that it is not the developing countries which are at fault. Now it is those developed countries who have contributed to this maximum damage to the global greenhouse gases, and they have to pay the entire expenditure. And that is when actually 100 billion US dollars per every year, a kind of a fund, green sustainability fund was uh, committed by the developer countries. Anyway, now let us go forward. So these are the important sustainability development goals. For example, every state has got, under the planning commission of Indian government, the statistics and planning department of every state naturally becomes a part of United Nations sustainability development goals. And in Karnataka also, the statistics, planning and statistics department, the government department, is directly responsible for the sustainability development goals and their monitoring in Karnataka. So as civil engineers, we are not, though we are not directly connected with several things, but majority of the 6 goals we are connected with. Now, for example, these 6 sustainability development goals, starting with quality education, for example, sustainability development goals for quality education. Now, the new education policy touches upon several improvements and then several changes, modifications, and believe me, they are all based on the sustainability development goal number 4 and sustainability development 6, clean water and sanitation. The next goal number 9 on industry, innovation and infrastructure, sustainable cities and communities, which relates to goal number 11, and then climate action on goal number 13. So these are the actually 6 goals where civil engineers are directly connected with. So please remember, we are not away from that. Now, in what way these buildings and then are important? Buildings interact with the environment in various ways. Throughout their life cycle, they consume resources in the form of energy, water, materials, etc., and emit several greenhouse gases. So we say that only carbon dioxide is the greenhouse gas. It is actually, there are several other greenhouse gases, 6 other important greenhouse gases, but carbon dioxide, they're all converted in equivalent to carbon dioxide. That's why we call carbon dioxide as one of the important greenhouse gases. But in general, we call it as carbon footprint. So when we talk about carbon footprint, it is actually not carbon alone, it is actually carbon dioxide which implies. So civil engineers endeavor to minimize a building resources. So buildings form actually an extremely important, or play an important role in reducing the carbon footprint or in reducing the greenhouse gases and greenhouse gas emissions. Buildings are responsible for greenhouse gas emissions, as you can see from the side boxes. Indiscriminate use of natural materials, we are responsible. So entire construction process is absolutely energy intensive, resulting carbon spike phenomena. We will see forward what is carbon spike phenomena and in what way buildings are responsible, and in what way carbon neutrality is the future of the buildings. Now, buildings are responsible for almost about 40% of the energy use, the total energy use. Now we are talking about in Indian perspective, and an estimated 42% of the global water consumption and 50% of the global raw material consumption is by buildings. This also applies to India, approximately the same percentage. An estimated 50% of the world's air pollution, 42% of its greenhouse gases, 50% of water pollution, 48% of solid waste, 50% of chlorofluorocarbons, all are due to built environment and buildings and infrastructure. Global emissions, which have to be cut by 2030 for life. And when I say global emission, this 30%, this 50%, which is actually applicable to every country. So when it comes to India, we also have to be cut to half. To our production, our emission to be cut to half. The lower carbon economy is a $26 trillion opportunity. Now, it is just not reducing, but actually when you convert all these things into business opportunity, even for a business opportunity, it is a huge business opportunity to become sustainable. That is because there are a lot of innovations are happening. Youngsters now are going several innovative ways how to reduce the carbon footprint in building. Now, if you take the global top three countries, uh, this is the scenario in which total emission in gigatons, China is 10 gigatons, USA 5.41, India is 2.65 gigatons. Total emissions, China 30%, USA 15%, India 67. Now you will wonder actually, China, USA, and other European countries all put together, they emit almost 61% of the global greenhouse gas emissions. India's contribution is only 7%, but we need not be very uh, happy about that. Our contribution is 7%, but it is getting multiplied because of the population, and very soon we will, we will overtake everybody, unfortunately. And global footprint, these are all interest of the data, which and believe me, we consume 17% of the fresh water that is available globally to us. This is, and if at all there is going to be a third world war, they say it will be for the water. And so 17% of the freshwater consumption is being one of the footprints which consumption consumed by buildings. Now, what is global warming? I'm sure now I will not spend much time on this global warming and greenhouse gas effect, because so it is just, I'll just read through, is a gaseous compound. Global greenhouse gas is a gaseous compound in the atmosphere that is capable of absorbing infrared radiation, thereby trapping and holding the heat in the atmosphere. Because of this accumulation of the greenhouse gases in the atmosphere, there is a greenhouse gas effect, and then we are facing this global warming. And these are the very simple things where you will I will now, this slide is important. No, all these on the top one, what you see are the important greenhouse gas, which I said about 6. So carbon dioxide, methane, nitrous oxide, etc. These are, if you see, for example, carbon dioxide and hexafluorides. Hexafluoride, if you take a global warming span of about 100 years, it's almost about 23,900 times worse than carbon dioxide. But even then, we take carbon dioxide as one of the primary greenhouse gas emissions, because carbon dioxide lives in the atmosphere for almost about 140 years. Now, let us say today or tomorrow, we say that, for it's just a hypothetical case, all the world stops the carbon emission of greenhouse gases. Now it will take almost to the tune of about 115 to 140 years to effectively get a carbon dioxide free, greenhouse gas emission free atmosphere. So this period is called as lock-in period. So you don't be happy. So that means we need to work 140 years greenhouse gas emission completely, continuously. So you can imagine the amount of that is the reason why all gases, whereas all the other greenhouse gases other than carbon dioxide, they have a very short-lived life in the atmosphere. That's why all of them are converted to equivalent to carbon dioxide. That is why the unit of carbon dioxide is in terms of kg CO2 equivalent, in bracket E they write per kg. So everything is converted into equivalent. So now these otherwise, so this, it is called GWP. So then it is a GWP of carbon dioxide in a span of 100 years is taken as 1, and for that of methane is taken as 26, and these are all the ranges which are there. And sulfur hexafluoride, all these PFCs and then HCFCs, what you see, they are actually for example, air conditioning contributes to all these fluorocarbons. So that is why now you might have seen the very highly efficient air conditioners and then air coolers or the tower air conditions. They all actually specify the fluorocarbon emissions, etc., etc. When they call it a sustainability of efficient air conditioners, they mean that they have reduced the efficiency has increased by reducing these these affect actually the ozone layer. So so this is a very important terminology to be remembered. Now, what is carbon dioxide concentration? We know it's all measured in parts per million, etc. I will not go into the details of it, but there is an important, see, the entire world so far is from since almost 1900 or so, earlier in 1900, there was a scientist called Keeling. So he invented a kind of an instrument which is now mounted, the sensor, which is now mounted on one of the Hawaiian mountains to measure the global average carbon dioxide emission or the concentration that is there in the atmosphere. So now that is taken as the world, that particular spot is the average carbon dioxide concentration, and that is represented by Keeling curve. That's why it's called Keeling curve. So yeah, as you can see from the graph, in 1960, it was 310. Anyway, in 1750s, it was 280 ppm, and in 1958, it is 320. When actually the industrial revolution and other things started, it was almost about 280 to 300 ppm, and within 100 years we have almost touched we increased by 100 to 120 units, and today we have almost touched about 450 ppm as of yesterday or as of day before yesterday. So if you start, actually the concentration increases to 550. Some people say that the human species will start bleeding through their nose. So that is the reason why air pollution also becomes extremely detrimental. Now, these are the tipping points. These are actually called the planetary boundaries, and these are the 11 important parameters which are there in the for the safety of this thing: climate change, ocean acidification, stratosphere ozone depletion, and all these things, global cycle, etc., change. These which you see in the periphery of the graph are the 10 or 11 parameters, and they are called actually the concentric circles in red, what you see is actually the boundaries. They are the planetary boundaries. Now, if you take the biodiversity loss, we have already lost, we cannot lose any more species. We have gone beyond that. The nitrogen cycle, we have already crossed the limit. Now, what you see in the red zone is actually the zone in which we are there, and then something little beyond that, or increase in the global warming temperature more than by 1% will cross all the boundaries here. Now, urban heat island, which I'm sure we all know this, and the more and more we cover, the more and more we create the hard surfaces, reflective roofs, heat from vehicle tops, vehicle services. You name anything, from there is a reflection. There is some amount of absorption, there is reflection. So this happens more in the cities and particularly in gated communities, and all these things, this phenomena actually cause island effects. Now, and frequently in the sustainability domain, you hear what is called as Agenda 2030. This nothing but Agenda 203 is by 2030, every country, as I said, should reduce its emission of greenhouse gases, and thereby help to reduce the global warming temperature, the warming warmth of the global temperature to less than 1.5 degrees. So that itself is the big agenda. Now, this I would like to come back to the national Indian carbon footprint construction industry scenario with respect to India. India, as I said earlier, Indian total contribution to the global emission itself is about 6.5 to 7%. And in this 7%, the construction industry contributes to about 40% of the total emission. And in that 40%, 70 to 80% is operative and maintenance, and the pre-construction and construction phases is 20 to 25%. And this 20 to 25%, the pre-construction phase, is completely neglected by civil engineers. So we think that sustainability comes into the picture only at the construction phase, but no. It is actually in the construction phase and pre-construction phase, it all comes into the picture. So that is why we have several green rating systems and all the other things which actually come into the picture. Now, what are the different types of constructions? Now we have linear construction method, wherein this is the construction, the conventional construction, what we are used to. Take, make, use, and then dispose. We are not really bothered about the wastage, whether how many times we use the formwork, how many times you use the materials, do we recycle the material, do we reuse the material? We are really not bothered. Even today, in general, the majority of the portions, we follow this linear construction method, which actually is a big no. Okay. And then there is what is called a circular construction. Circular construction is actually called also as a cradle to cradle principle, where the products and assets are designed and built to be more durable and to be repaired, refurbished, reused, and then dismantled. That means, for example, you construct a building, I use those materials and the specifications and then the qualities, the characteristics and all those things of materials, and use such materials after dismantling of that particular building or by demolition of that building. We should be able to reuse and then recycle those materials and into the building. So that is where from take the raw materials, you avoid picking up the raw materials and then the energy consumed for processing of the raw material, and all those steps will get saved. And then that is why from cradle to cradle principle, this circular construction attracts extremely high importance. Now there are also other principles and the construction methodologies which have come into the picture. They are under the process, and there is a process called BAM. It is buildings as material banks. In terms, for example, if we can design them in a steel building, for example, a PEB building, where everything, the material building is perceived as a material bank. The very concept of designing, at the designing stage itself, we take the building itself not as a building to be used, but building as a material bank. That means the way we take out from the bank, so these materials can be actually, can be recovered, reused, recycled, and then exactly from the bank lockers what we use. So this is the process which also comes into the picture. So now the mindset which has to be shifted from linear to circular, which actually is extremely difficult. The linear model, I will not explain it because it all is exactly what we are doing. Now, in terms of circular construction, what is one of the important factor is, in circular construction, all stakeholders are coming together in the beginning. Even before the building comes into the picture, when the drawings are, the design is on the board, then at that point in time, hello, is there any question?
No, sir. We have kept the question answer session in the last.
All
if
right.
anybody wants, they will raise the hand.
Okay.
Will not
Because
interrupt
I
you,
have full screen, I don't have that thing which is appearing. So please
Uh,
let me know if there are any.
yes, sir.
So,
Sure, we will
you
let you
know,
know, sir.
all the entire all stakeholders are coming together and getting involved. In conventional case, what happened? Only the owner sits and probably the architects sit, and even the structural engineers also come after everything is designed. No, in circular construction, this concept will go. Every vendor is important. Architects are important. Equally important are structural engineers. Equally important are project management consultants. Equally important are contractors who execute, vendors. Everybody is important because everybody can contribute to that project. So, or taking all those inputs, the project takes shape. The design of the project actually takes place. So that means the project design itself becomes more inclusive, more transparent. So we need to shift from, as a designer, as academicians, we need to shift our this mindset from linear construction methodology, even linear design aspect, to circular design and then circular construction. Now, there is also a method which is a framework to illustrate the application of the circular economy, and it is known as Resolve. You know, it's an acronym as Resolve, where regeneration, the first step is the regenerate, and then the second step is the share. Third step is to optimize everything that comes into the picture. Then the loop, which remanufacture, and 3R come into the picture. Virtualize, dematerializing, and then go virtual comes into the picture. Then replacement of the old and efficient materials, apply new technologies in exchange, choose sustainability, sustainable new product, and all these things actually come into the picture. So this is one of the new platform which is under production, and I will not get into the details of this Resolve, but just as an information, I would like to kindly please remember, and you can go into details subsequently. Now, I told you a little about the little ago about carbon spike, and the pre-construction and construction area is completely neglected. Now, in a project, the total, if you take the entire life cycle of a building, the probably the design life will be say about 50 to 60 years or 60 to 70 years. But a building constructed good, we don't even think of even demolishing it. As long as it comes, it comes. But let us take the design life as 60 to 70 years. And in that 60 to 70 years of a life cycle or a design life of a building, now construction period is hardly about maximum 2 years or 3 years, not more than that, right? So this PCP is pre-construction phase, CP is construction phase, and then uh, ONP is operation and maintenance phase. Now, this construction phase is the phase where we use the maximum materials, maximum embodied energy is consumed, and then maximum energy is consumed. Everything is extremely high in these 2 to 3 years when you compare it to the entire life cycle of a building of 60 to 70 years. That is the reason why it is said that 80% of the life cycle of a building, it goes only into operation and maintenance of the building. But the remaining 20 to 25% is the pre-construction phase and then construction phases. But it is this, during this construction phase, out of 60 years, this 2 years, you have extreme high energy consumption of the entire building, high embodied energy, and then high embodied carbon and all these things, and then and consequently there is an extremely high greenhouse gas emission, and that is the reason why this construction phase is called as the carbon spike phenomena. So the carbon spike phenomena is essentially a phase where extremely high consumption and then the carbon emission comes into the picture, and it is uh, mm, almost about 60 to 70% higher than the other consumption period. Now, what exactly is a comprehensive contemporary ecological design? or some people call it as comprehensive ecological design. Uh, Now, this calls for actually a significant level of knowledge, experience with selecting appropriate. Now, the civil engineers, this is going to open up a huge, this is already opened up. So, if there are any students or postgraduates who are listening to this thing, or the faculty members, please remember that this is one field which I have seen with my own eyes across the globe, that it is going to be one of the extreme. So you please consider doing your specialization, post graduation, doctorate in these fields where the demand is going to be extremely huge. So even as a private entrepreneur, your looking forward is going to be these fields are going to be the eye catchers in few, just very shortly. So energy trade-offs, wind direction has to be taken into consideration, sun path has to be taken into consideration, the passive architecture, building orientation, passive healing, passive cooling, passive lighting, ventilation, all these things have to be taken into consideration if your building has to be a, uh, a very comprehensively designed. If you take the elements of sustainable construction design parameters as per NBC 2016, these are actually the 10 elements of sustainability construction. Now, inclusive approach, not in parts. This is what that means. It is not linear construction as we discussed. It has to be a circular construction. The use of technological advancement, use of technology and advancement has to be incorporated into the entire design so as to minimize or optimize every resource that is available. Manpower resource, the material, everything, all resources have to be minimized. Buildings as material banks, which we already discussed. Minimum natural resource consumption, that means unnecessary factor of safety need not be this thing. Thumb rules should be very optimized. We don't now afford that kind of a liberal utilization. For example, I keep saying there is no point in importing marble from Rajasthan and using it in a South Indian house rather than using granite. Or, for example, in Gulbarga and those areas, not using the locally available Shabad, Kadapa, and all those beautiful slate material, but bring all the marble all the way from Rajasthan and then using it. This exactly is the minimum natural resource consumption. You minimize, you utilize the locally available material. Quantify and manage impact assessment. How for everything, if a material has to be transported, what is its impact? If material has to be not to be wastage to be used, what is its impact? It's everything. Performance versus benchmarking values is also extremely important. But unfortunately, this doesn't happen. Now, every architect, every designer wants his special effect on the building, so it is not taken into consideration. So clients also want it. So we are completely going against the very principles of sustainability. Adaptable to climate zone, geological conditions, human and health comfort. Also, ultimately, why do we design for? Buildings are designed for what? For people to stay inside. And do we want them to stay happily, well, healthy, or not? Obviously, we want it the good health. So human health and human comfort becomes absolutely important in the building. Taking that address already, I have already addressed the lock-in period of the environmental impact, which has to be taken into consideration. Make use of traditional wisdom in designs many times. Many a times, for example, using red oxide flooring, all those beautiful flooring which appears, we have lost the labors, we have lost the specialty, but instead we use extremely high embodied energy materials. And these are the uh, traditional materials, traditional wisdom, that wherever it is possible to use it, we need to bring that into consideration. Obviously, for multi-storied buildings, high-rise buildings, there every building has got its own uniqueness, and every building has to be treated separately with an individual sustainability discretionary thought into while designing the entire area. Now we come to the once we have studied these in the last slide when we studied these 10 elements. Now let us go into the what exactly are the construction parameters, and then now we in the life cycle analysis, which one do we adopt? What exactly is life cycle analysis? We studied. We take the entire life cycle of a building, starting from a building, whatever the materials require. I think I will read this here, it will be a better thing. Life cycle analysis is a method of assessing the sustainability levels of buildings or infrastructure projects from pre-construction phase to demolition phase, satisfying the circular construction principles or the cradle to grave, cradle to cradle principles. Uh, then now we have three methods of life cycle analysis. One is the process analysis, which actually involves the data related to each of the processes, starting from raw materials extraction and non-availability of reliable. Now here, the full data to the entire thing is not available to us. It's extremely difficult. Who will keep the idea how much of raw material was used for preparing the tile that is used in my house? That data will not be available. It's very extremely complicated process. That is. Then the second one is input output analysis. This particular process or the methodology captures and derives data from several resources, including the data from the economic sectors. Hence, this also becomes extremely complicated because the data will change, keep on extremely dynamic. The economic conditions are so. This is also has its own limitations. There is hybrid analysis, which actually takes good points and then from the where the probable points where the data can be arrived. So this process, this hybrid analysis, as a methodology of analyzing the life cycle analysis, is considered as is most commonly being used and very widely accepted also. So when we generally talk about life cycle analysis, henceforth in the project, in the presentation, it is basically I have considered hybrid analysis in the entire design concepts. Now, now we are coming actually to some of the important terminologies which become important. What exactly is embodied energy? Embodied energy is the total non-renewable energy that goes into the manufacture of material from its extraction till it is consumed. There is the entire life cycle of a material. Suppose I want to understand the life cycle of a tile. Now, what is the life cycle of a tile? When the life cycle of a tile is right from the clay extraction, what it goes, the other materials which go into manufacturing of the clay, the way it is extracted, the energy that is consumed during the extraction. There might be several mechanical equipment may be used. The fuel energy, the electrical energy. Fuel energy is also one of the energies which has to be converted into the energy consumption and then taken into consideration. So all these energies put together, and when the tile raw materials come into the factory, then it is the manufactured, processed, filtered, packed, and then delivered delivered to the site. So transportation is involved. So till it comes to the use of the building, it is the life cycle story of a tile. Now, this is the life cycle of each material takes into consideration. And then when you take the embodied energy, if there are about 50 such different materials, it is the combination of all these materials which actually gives us the embodied energy of that particular energy. This embodied energy also gets classified into three different embodied energy. One is the initial embodied energy, which is the energy consumed in the process from the acquisition of raw materials to the construction. Recurring embodied energy, which is actually very important. It is the energy consumed during the maintenance or livable use phase of the building. Suppose we may have several gadgets, let us say kitchen gadget. how much mixer I use, how many fans do I burn, how many lights do I burn, how many air condition do I run. So all the energy that is consumed during the design life of a building is the recurring embodied energy. And then the last classification is end of life of energy. That means when a building is either disposed or actually demolished, what kind of energy that is required to demolish that building, and then to recycle or reuse those buildings to extract those reusable materials which come into the picture. So this is the end of life energy. So actually in combination, initial embodied energy, recurring embodied energy, and life of energy is the total energy input footprint of the life cycle of a building. So embodied energy is not just one simple energy, that is not just a value. As an engineers, we have to take all the three classifications, three types of energy into consideration. Now, what is embodied carbon? Embodied carbon is the carbon footprint of a material. It considers how many greenhouse gases are released throughout the supply chain. So the way embodied energy consumption is calculated in embodied energy, similarly, how much carbon dioxide is emitted in each process, that gives an idea of embodied carbon. Embodied carbon, as I told you, is expressed in terms of kg carbon dioxide per kg, and in terms of embodied energy is expressed in terms of megajoules per kg or per unit. Uh, Per kg or per cubic meter or per unit, everything can be ultimately converted. Now, this is once we understand the embodied energy and embodied carbon. See, there are actually there is a beautiful concept. We can actually apply only use this embodied energy and then embodied carbon itself to understand the status of a building. So far, have you understood? Is there any doubt, participants? I hope everything is uh, getting clear.
Yes, sir.
Embodied energy stay ಇರಬೇಕು ಅಂತ.
Yeah.
Embodied
Now,
energy stay ಇರಬೇಕಂತ ಏನಾದರೂ ಪ್ಯಾರಾಮೀಟರ್ ಇದೆ?
ಅದಕ್ಕೆ ಹೇಳ್ತೀನಿ.
okay. Now let us come to the example. Uh, Now, how do I know? This is just to break the monotony or this thing. Now, you know this Antilia Mumbai is the world's most expensive home of Mukesh of Ambani. Now, everybody is interested. How much? For me, it was just sheer interest. How much? What is its sustainability impact? And I did calculations only. I mean, these data is not available. Actually, these are all called as iconic structures. We actually cannot calculate. They don't even come anywhere near the sustainable projects at all altogether. For example, Burj Khalifa and these kinds of structures, the renowned structures which are built for the tallest, the widest, the biggest, the smartest, the costliest, all these things actually are beyond sustainability calculations. So, but just out of academic interest, these are the details which are available on the internet. The Ambani house is almost about 4,550 square meter is the plotter. All these details are available on the net. So this is nothing anything confidential or anything. These are the data collected from the internet. So the number of floors is 27, etc. All these things actually come into the picture. Once you take this consideration, now look at it. The total construction area of the construction of the house is 4 lakh square feet. Dear friends, it is approximately 8 acres of construction. This house is 8 acres of construction. Please believe it. And the total cost of the project is 13,000 crores, which amounts to about 3 lakh per square feet. The house has got 6-floor car parking floors for 168 cars, 50-seater theater, swimming pool, spa, artificial snowfall room, helipad, then air traffic control floor, etc. Now, how does it calculate from the embodied energy and then embodied carbon content itself? Now, the cost of construction So cost of construction per square meter is approximately 2.86 lakh square feet or 3 lakh square feet. Now, what is the total embodied energy of the entire building? Now, this building has, I will tell you how to calculate the embodied energy in just few slides, but just imagine that how, like this, I said megajoules per kg or per unit we need. So this house is expressed in terms of uh, gigajoules, that is megajoules multiplied by 10 to the power of 3 gives you gigajoules. So 3,36,510 gigajoules is the energy consumed for the entire building. Now, when you convert that into electricity at the rate of 10 rupees per unit rate, energy consumed by this building approximately is 92 crores. That is 100 crores is the embodied energy in terms of commercial value of this building. So similarly, the embodied carbon is about 33,000 tons of embodied carbon. Each ton approximately, you can think that per cubic meter it is about 0.5 per ton of carbon dioxide occupies about point half a cubic meter of space. So almost 1 ton of carbon dioxide occupies 550 cubic meters of space. So this particular building has occupied a carbon dioxide, concentrated carbon dioxide, to the tune of about 265 meters by 265 meters by 265 meters of space. So which itself is a huge impact on the climate, this thing. So now let us come to, just 1 second. Yeah. Now this is how we calculate the, based on the, as an example, out of shear, you can take any building and then calculate using the embodied energy and embodied carbon. Now, then what are the other ways to calculate embodied energy, the comparison, whether my building is sustainable or not sustainable? Then we have actually we need to understand that there are buildings in India, and for us to compare, which are actually extremely sustainable buildings. They are multi-storied buildings. They are framed structures, but in spite of them, they are extremely sustainable. So we need to take, benchmarking is one of the important aspects specified by the UNDP, the United Nations Development Program, and also UNEP, United Nations Environmental Program. So benchmarking of buildings provide a set of measurable baseline values which will actually facilitate us the improvements in the overall energy performance of a particular building. See, in this figure, what you see, we see two figures. They're simple buildings, but actually extremely elegant. The bottom one, you see an extremely elegant conference hall, standalone conference hall. And this is one of the buildings what we see. So we need to understand the baseline buildings also. And there are what are known as the green building ratings also come into the picture. And please remember that all these green building ratings are all criteria based ratings. That means we do rainwater harvesting in a project, we get so many marks. We use sustainable materials, we get so many marks. So these are all criteria based. No doubt, by following green rating systems, it could be anything. It could be IGBC, it could be USGBC or anything. There are several greenhouse rating systems. In India, in the world, approximately there are about 64 green rating systems. And in India, we have several rating systems are being used. HK Beam, which is from Hong Kong. UK BREEAM is also being used. Singapore Green Mark is being used in India, greenhouse buildings. But IGBC, Griha rating from Terry, IGBC and USGBC, these are very well accepted green rating systems. Now, these are the just criterias. If you go through the green building rating systems, these I have just taken to give you an idea. In terms of Indian Green Building Council, how do they actually rate a building? These are the different criterias which uh, you can get all these criterias on a net if you just say IGBC rating criteria. So I will not go through these different in detail because it's due to paucity of time. Now, so when you get these lead rating systems, now let us say your benchmark project. Just few minutes back, I talked about establishing a benchmark project. So now that benchmark project has to be validated by the several green building certification. So the example what I'm going to discuss with you in few slides more is actually has been validated with reference to the lead certification and also IGBC certification. So BMP is a benchmark project, DMP is a demonstrative project. So this benchmark validation is also actually done. So you can actually see here the total criteria for a platinum rating of IGBC, for example, is this sustainable sites. So total 75 points you need for actually platinum rated IGBC building. So the benchmark building what we have taken has earned 71 points, which means to say that the demonstrative project which we have considering as benchmark project has achieved a credit platinum rating as per the green rating system criteria which has been taken into consideration. Similarly, we can take green low energy buildings, etc. Somebody was asking me how much should be is there any criteria how much it should be, etc. See, there is no fixed criteria how much building should be there is no fixed criteria, but there are classification which I'm going to now discuss. Actually, the next 30 minutes is going to be actually a extremely technical and extremely fast this thing. So we will understand all the things. These are few. Actually, for example, this particular building, the embodied energy is only 2,460. For example, as compared to this particular configuration of a building, suppose you construct the same building using RCC structure, it goes to 5,000 to 7,000 megajoules per square meter. And embodied carbon also, it goes to 500 to 600 kg CO2 per kg. So there is no specific range which is evolved, but there is a classification which is available to us. These are few of the examples of low energy building where we can see the thing. Now, I will give you quickly rush through 12 important steps required for sustainable construction. How can we design the sustainable construction? Step number 1, we need to preliminary performance peg the details of the performance targets. That means what should be in my energy consumption, what should be my water consumption, what should be the type of material I should use, what will be the economic performance, what are the different construction practices, what do I do with the waste, how do I optimize the waste, and how do I give the best indoor environment quality, landscape. All these things will have to come into the picture, and the targets, and then the pre-construction phase design has to be done. This is where the circular principle come into the picture, because all these things require vendors' inputs also. Just the owner or the architect or the primary designer will not be in a position to give inputs for all these things. That's why circularity principle calls for extremely transparent involvement of all the engineers and all the stakeholders. Now, the second step actually is you need to protect or enhance the site's ecological integrity and biodiversity. It basically you try to minimize the development footprint. Suppose, let us not construct from compound wall to compound wall and claim very big that we have achieved maximum coverage, or by deviating and akrama sakrama and utilizing dirty schemes like akrama sakrama and all those things. So, but reduce the footprint. And I was just happened to be with Abdul Kalamji. I had an opportunity to spend about 4 hours one-to-one with him. And then I asked him this question actually: how do you, in your own terms, how do you define sustainability? He gave me an absolutely fantastic definition. He said, sustainability is actually a thin line drawn between need and greed. It answers the whole thing. We actually, out of greed, if my requirement is 1000 square feet building, I construct 4000 square building. So this actually is the line to be drawn between the need and the greed. So this also applies to the various other site conditions. And the third step actually is reduce or eliminate disturbance to water system. That means if there is a valley, we are not talking about just simply 30, 40 sites or 40, 60 sites. We are now talking about the huge infrastructure projects where there is a land acquisition takes place. For example, we all see what happens in Bangalore. Lakes get occupied. This is one of the important criteria, that we should not disturb the water system that is actually available. And there is a way in which the nature has almost found its stormwater runoff and other things. Minimal disturbances has to be caused. And not only this, we need to actually, the entire water system also, while separators for oil and water separations to be done, designing the roads and parking roads without the curb, so that the stormwater, the runoff from the roads can get collected to the site. All these things have to be taken in a nutshell. We need to reduce or eliminate disturbance to the water system. And step number 4, prevent or reduce the complete potable water irrigation. We need to start using the water to the maximum extent possible. Recycled water, reused water, water efficient plants have to be. It is just not from the water utilization itself. The rainwater harvesting comes into the picture, water efficient plants which are there. This is where the science and innovation and technology comes into the picture, where the native species can come into the picture. Use water efficient irrigation systems, micro irrigation, moisture sensors, etc. All these things have to be brought into the picture. Then step number 5, reduce urban heat islands. That means maximize the green spaces, and then don't cover unnecessarily around the building. Keep it as open as possible. Maximum pervious surfaces. Use those materials which are pervious. For example, the new generation concrete comes into the picture. The pervious concrete comes into the picture. The blocks come into the picture. So we can use several materials which can make these hard surfaces percolation, and we can use those surface area of these absorbable water, pervious water surfaces can be increased. So the green and heat island effect can be reduced. Step number 6, use existing and proposed trees, and for the plantings, if they are grown up trees, try to replant it and then transplant. Orient the buildings to optimize so that means we are now actually talking about the passive architecture. Orient the building to wind, taking the sun path into consideration, wind path into consideration, and all these things you need to take into consideration using the existing topography which can be done. Step number 7, design for flexibility. Design the structure. There is a cardinal principle in architecture or designing that means form follows function, function follows form. We need to be not only that, but what we need to follow also, we need to design the structure to be more resilient, more flexible. Design a structure that allows for changes in use forever. I may design a building today. I may begin a theater, build a structure as, let us say, Kalyana Mandapam or a marriage hall. And then we have seen in Bangalore, we have seen many of them have been converted into theaters, or theaters have been converted into marriage halls. So these are the things which we need to take these things into consideration. Instead of demolishing and then rebuilding that construct, the designing should take into consideration the flexibility also. Then also for design for disassembly, which I already talked about, we need to select those materials which can be disassembled and then reused very frequently. Step number 8 and 9, reduce heating, cooling, and then optimize everything, configure the internal layout to reduce the loads, enhance indoor air quality, indoor environmental quality, and energy consumption. That means we have several gadgets, several things which are coming into the picture, absolutely important things that are happening. We need to reduce heating, cooling, lighting, ventilation, etc. Then locate internal spaces which to optimize natural ventilation. Users that do not need windows can be located on the north side. All these kinds of things can happen to configure and configure the internal layout to reduce the loads. Now, for example, if you take the commercial buildings in Bangalore, every building, 90% of the buildings are covered with glass facades. I really don't understand what is the need for the glass facades in Bangalore, other than the aesthetics part of it. Now, what happens is Bangalore really doesn't need it doesn't need glass facade. Now, it is only for now. Once I use the glass facade, then the heat transmission is more inside. So I use more of air conditioning, central air conditioning utility goes up, energy consumption goes up. Now, to prevent that, I am using double glazing. That means now there are the glass manufacturers come into the picture, vacuum is created, and then there are actually colored glasses come into the picture, glazed, tinted. So that means we keep on finding innovations, just keep on increasing the cost, increasing the building, increasing the energy consumption. Yes, wherever it is required, please use it. It is not going against the principles, but to the extent possible, optimization becomes the mantra. Optimization becomes the mantra, and it becomes, as a profession, it becomes our responsibility as engineers, as designers, as architects. It becomes our responsibility to convince our clients actually which is more helpful, more aesthetic. And good thing is that lot of awareness is happening, and then many of the clients actually are coming out with these requirements. More and more green awareness is happening, and we need to use, as far as the paint is concerned, we need to use low VOC materials, use structures that do not require finishes that emit VOCs, etc. Then step number 10, design the envelope. That's exactly what I talked about, designing the envelope to bring the daylight in views. So designing the envelope means the entire outside wall, outside portion of the building, which the barrier between the external environment and the internal environment is the envelope. As the definition it goes. So now envelope doesn't mean only the walls. Envelope takes into consideration all that which wraps the internal environment. That means roof comes into the picture, waterproofing comes into the picture, side walls comes into the picture, the basement comes into the picture, below the floor comes into the picture. So all these actually form the envelope. So all these, the entire, when we talk about envelope design, we talk about the entire envelope design has to be. Facade is one of the envelopes, important envelopes in terms of commercialization. How do we minimize that environment? So this envelope design itself is one of the important criteria. Now, for example, this particular building, what you are seeing now, is just a sample building which is done under the guidance of United Nations, following the United Nations circularity principle into consideration. It's a two-storied building. ground and first floor with the vault construction on the roof. It doesn't have a flat, no air conditioning, no fans inside, but there is a difference of about 10-degree temperature inside and outside the building. And the embodied energy of this building is only 2,800 megajoules, whereas the equivalent building in the conventional way will go to about 5,000 megajoules per square meter as the embodied energy point is concerned, and embodied carbon is concerned. This is only 360, and the conventional building will enhance the carbon, embodied carbon, to the tune of almost about 600 to 700 kg CO2 per kg. Now, the designing in the envelope to bring the daylight and views to as much of the inhabited floor area as possible. So designing of the envelope becomes extremely important also. Now, building envelopes is the one which I have talked about, which I said the solar, the roof is concerned, the foundation, the walls, everything, and the interaction of the external environment into the internal environment should be studied. What exactly is the difference? What is the barriers? What is the function of the barrier? Is it only heat transmission to avoid heat transmission, or is the external environment is extremely moist, and then is it to trap the moist? These are the important considerations which and these things. So we need to design the walls, we need to design the roof, we need to design the fenestration, that is the openings, the doors and windows, the joineries, the floor, the surface finishes. All these things have to be taken into consideration when talk about the building. Now, step number 10, we already talked about the good indoor air quality. And air quality encompasses factors as maintenance of acceptable temperature, good indoor air quality plus the indoor environmental quality also have to be taken into consideration. That is acceptable temperature, relative humidity, control of airborne contaminants, and then because of that's why it is advisable to use low VOC, and then adequate ventilation, etc. All these things actually come into the picture. Now, step number 11 is actually the accumulation different, as I said, first reduce the ozone depletion. That means reduce the usage of air conditioner and the entire optimization of HVAC system itself. Eventually, then installing alternative wastewater technologies. How can we reuse the water? What kind of treatment plants can be this thing? How rainwater can be used? All these things actually can be done. The rainwater harvesting, how can we replenish the water? And all these things actually, all major building system designs should be documented for commissioning these things into consideration. So that is why in the circularity principle, more than the construction phase, all these things which actually happen in the pre-construction phase and the construction phase become actually into the most important thing into the view. Now, step number 12. Now, what exactly are the alternative building materials? Now, which material should I use? This is the question which always comes into the picture. I will not go into the material. There are several materials, but most of us know what exactly are the materials. Just to tell you, in between the concrete hollow block and then concrete solid block, which is better? Which concrete block in terms of embodied energy and embodied carbon? That should be compared with the tables. There are a lot of tables which are available, which will give you the values of embodied energy, embodied carbon, etc. So from those two perspectives, choose those materials. And then now low embodied energy materials to be chosen and maximize. So for example, instead of concrete blocks or hollow blocks or even the clay bricks, so bricks have got, if it is heated, and then it becomes much more it doesn't become sustainable. Bricks are not sustainable. Only soil compressed blocks which are not heated using or by burning the coal are sustainable, which is used at site, manufactured at site. They are sustainable, not the bricks. So The other part is, suppose you use fly ash bricks, they're definitely more sustainable. So instead of fly ash bricks, and if you want to use in between, then aerated concrete blocks which come into the picture, which actually meet all the compressive strength criteria, the durability criteria, and then the volume. It is light in weight, and because the block is like aerated concrete block is light in weight, your load on the structure becomes design load on the structure becomes light, so the entire structure will become light. So the reinforcement, everything, the entire, it impacts the entire quality. So it is the discretion of the engineer for the purpose which he's constructing the building becomes absolutely important. Whether do I use these aerated concrete blocks in the outer envelope? That's why I just told you the outer envelope, the functioning of the outer envelope is most important. So in these circumstances, for every material, this kind of analysis has to be done. So this is the alternative building materials have to be chosen. Now we have BMTPC, which is giving us several materials in place of bricks. What are the other materials? In place of aggregate, what are the recycled aggregates? In terms of cement, I have seen many clients, sir, we want to use the best quality of cement, highest grade of cement. As he as a client, he wants to show that by spending more money he gets extremely good quality rubbish. We as engineers and architects should tell him what is the difference between 33 grade, 43 grade cement and 53 grade cement. We need to clearly explain what is the difference between OPC and PPC cement, what is the difference between virgin steel and then recycled steel. All these things actually have to be used, and it is the discretion of the engineer which comes into the picture, where to use the recycled steel. For example, in secondary use building, for if it is a manhole cover where why can't we use the second recycled steel? Okay, the virgin steel can be used in the primary elements of the structural elements of a building, but all other places, chajjas, for example, sills, lintel beams, all the brick the bands which actually are adopted in between the masonries, the pavements, the flooring, where the vacuum parking area, all these things, for example, the recycled steel can be used, and then we can actually use these alternative materials for the discretion. Recycled aggregates, where do I use the recycled aggregates? The brick bats, where do I use? All these things have to be, I suggest the members here to study National Building Code in detail and then go ahead with these things. Now I will come to the classification of the materials. Though there is no specific guidelines that how much it should be, how much it should not be, there is a classification of materials based on energy intensity. If it is more than 50, it is greater than 50. For example, aluminium, stainless steel, plastic, copper, zinc, brass have got highest embodied energy. Now, this is called actually very high energy intensive. Now, high energy and between 5 and 50, cement, steel, glass, bitumen, all these materials actually come in high energy materials. Medium energy, we have lime, gypsum, plaster, burnt clay, etc. Aerated block, fiber board, cellulose insulation, in situ concrete, all these come into low energy materials, which is less than 1, sand, aggregate, stones, fly ash, all these waste products which come, the material that is manufactured using waste, that becomes a low energy material. Now, as an engineer, you need to understand and you need to design your buildings. Where do I use high energy materials, low energy materials, medium energy materials, high energy, very high energy materials? For example, if I ask you a question, aluminium, let us say aluminium has got the highest embodied energy. Now, is using aluminium windows good or bad for a structure? Definitely, from the embodied energy perspective, using aluminium windows is not sustainable. But as an engineer, Now, I know aluminium is lightweight. I know aluminium doesn't need much maintenance. I know aluminium doesn't need any repair work at all. Aluminium can be recycled and reused to the tune of almost about 85%. If it is recycled, once it is removed, its extrusion can be reused, and then when it is transported, the per kilogram for aluminium, the transportation impact also is extremely less. When taking all these factors throughout the design life of a building, aluminium window becomes sustainable. And please remember, our analysis is throughout the life cycle of a building, just for example, or of an infrastructure or of a project. It is not just only for next 2 years or 3 years. So an engineer, as a designer, our entire construction process should take these things into consideration. For example, the block work. Yes, use internal, wherever internal walls are there, use fly ash bricks. If you want some aesthetic walls, you can afford to use. It does Sustainability or a sustainable building is definitely not a cheap building. It is a myth. Some people think that sustainable building is a low cost building. No, big no. A sustainable building is not necessarily to be a cheap or low quality building or low economically low building. So let that be uh, clearly explained to your clients. So this is the classification. This is on the energy basis on which we can do. Now we will come to I have another 30 minutes. So we will actually come to very interesting case studies in this building. Let us now, I told you that there are a lot of tables where we get these values. This is out of academic interest. Now, what you are seeing on the screen is actually a embodied energy, embodied carbon table called Inventory of Carbon and Energy, published by Bath University, and it's a joint venture with Institution of Civil Engineers, UK. Now, this is every year they take the entire global scenario into consideration, and then the average values of different materials are used. Now, for example, you get, I have just taken aggregate. Okay. Now, for aggregate, you have embodied energy of zero point 0.1 megajoules per kg and embodied carbon of 0.05. Whereas for aluminium, they give you complete details of for different types. What is if new aluminium window is used, for example, extrusion is used for windows, it comes to 218. Kindly focus on my cursor if it is visible to you people. So under this embodied energy, under virgin aluminium, the embodied energy is 218. It actually stands the highest embodied energy among the material. Suppose you use the same recycled aluminium, you see the difference, it is 28.8 as against 218. Similarly, embodied carbon values are here. So for all the materials, including concrete, bitumen, brass, metal, everything, you have these embodied carbon. You can actually download this. This is a free download available. You just type download PDF inventory of carbon and energy. You will get these values. This is extremely beautiful. So these are the tables. And not only that, for every material, they give actually material profile. They give different data, different characters, and what exactly is its impact. Everything, and what is the standard deviation also they give you. So, and for example, cradle to cradle boundaries, what will be if you want to analyze the building from cradle to cradle, or what we spoke about circularity principle, the standard deviation is about plus or minus 20%. So all these details, it's very difficult to explain this one particular page itself, we can explain, talk about hours together. So kindly go through these, download that document, and you will be able to see all these documents. It's not very big document, 50 to 60. Now, as academicians, you would be interested, how do we calculate embodied energy? So I have taken 200 M200 concrete. How do we calculate from the, so we all are used to rate analysis. We know the density of materials, we know all the physical properties of mechanical properties of the materials. So based on that we can calculate. Now let us take M200 concrete per cubic meter. Now approximately I have considered 400 kg per cubic of cement is required per cubic meter of M200 basis. Now, as per the inventories of what we saw now, from the table, you see that for OPC, it is about 4.5 megajoules per kg of cement. Now, so for 400 kgs, you get 1800 megajoules per cubic meter. And similarly, for coarse aggregate, you get 166.5 megajoules. And then for finer aggregates, you get 129. So transport and cement, that also transportation is also involved in the cement. So they add for the cement transportation. This also is the figure which is given in the inventory table. That is why I have added this. If you add that with respective calculating proper units, you actually, the unit of transportation is 0.00285 megajoules per kg per kilometer. So you need to be very careful in calculating the units. So then you add about 10% miscellaneous activities. Now, so total megajoules per cubic meter, total embodied energy per cubic meter of 200 concrete is 1.06 megajoules per kg. I mean, if you divide it by the density of the concrete, I have taken 2400 kgs per cubic meter here. So if you divide the total megajoules of 2493 by 2400, which is the density of the concrete, you get 1.06 megajoules per kg. This is from the basics we have gone. Now, if you cross verify it, whether my calculation is correct or not, as per the inventory tables, it is 1.1 as the inventory table. What we are actually getting from the local details parameters, we get 1.06 megajoules per kg, which approximately is same as 1.1. So our calculations are correct. So similarly, if you add water to it, water we have here, we have not added the water. If you add the embodied water, this also embodied water, see, it is taken as 14 megajoules per kiloliter equivalent energy consumed. So you need to calculate per how many kiloliters of water per cubic meter of M200 concrete. If you take the life cycle analysis, as per the tables, they say if it is almost about equivalent to 141, 10.13 kiloliters of water is required to produce M200 grade of concrete, including the curing of concrete and other wastage. So which amounts to 141.82 megajoules. So this embodied carbon, embodied energy, because of embodied water, to be added to the previous embodied energy of concrete, which was 2493, and to you add 141, which will give you 2635.52 megajoules per cubic meter of M200 concrete. So this way we can actually while doing WBA, that means it is called as whole building analysis. I'm just giving you an example of M200 concrete. This way, there are about 600 to 700 items. Your actual detailed designing part evolves at least basically on that or the 10 or 12 primary parameters which contribute to the sustainability. Now, similarly, we can actually calculate on the basis of embodied carbon. Similarly, you can get the embodied carbon. I will just rush through this. And now, we just calculated, took the example of materials. How do we calculate for the material? Now, let us say building doesn't consider only the materials. Now, it considers, let us say, how do we calculate for the formwork? Now, let us take a formwork of shuttering of about 5 meters by 5 meters. You have, these are different plates, formwork plates of different sizes, 900 by 600 mm. All of us are used to this conventional formwork system. Now, there are conventional formwork system which use MS floor plates, jacks, and then adjustable jacks, then steel props, etc. And then there is also a formwork system which completely uses the plywood system. You know, the entire floor also used by ply, etc., and all those things. Then there is a aluminium formwork system, which we call as monolithic formwork system, where majority of the multi-storied buildings or mass housing, etc., we see all those things. But these are the three systems which we consider. And if we analyze these three systems from embodied energy calculations, from embodied carbon calculations, we can actually calculate all these. I will just show you this example. Now, for example, by embodied energy calculation, this thing, if you take now the conventional formwork system, what does it include? It includes MS floor plates, MS spans, jacks and props, silver or oak for the supporting. We don't use for everything. So this is the combination of conventional formwork system when we use. So we need to calculate how many numbers of them, what will be the total quantity, what will be the unit weight, what will be the total weight, and then per total weight in kgs, and from the tables, which from the inventories, what will be their megajoules embodied energy per kg and the total embodied energy. So for the formwork system, conventional formwork system of 5 meters 5 by 5 meters, the total embodied energy is coming to 80,334 megajoules per per total 25 square meters. So per square meter, if you actually calculate, it comes to about 3,213 megajoules per square meter. Similarly, embodied carbon also are put in this value, and they can also be calculated. Thus, we can actually calculate for the embodied energy for the conventional building, and then decide, once I have this, then let us say we work out on for the plywood formwork also. Essentially, MS floor plates in the formwork will be replaced by the plywood, and what will be the plywood total embodied energy? See there, you saw it as 3,000 embodied energy per square meter of conventional formwork was 3,213, as against now here a plywood formwork is reduced to 2,822. Why it is reduced? Because the same formwork, the number of repetitions are more, the wood has got less embodied energy, the finish is much better. Now, the aluminium formwork, if you take, or what we actually, there are many names are used, aluminium formwork or monolithic formwork. What we see, all the entire floor is cast together. You would have seen in the multiple where the mass housing takes place, all these areas, each floor is cast at a time, where you see all the walls and other things, everything is concrete. That kind of a formwork is used there. Then you will find suddenly reduced to 1,700 megajoules per. This is mainly because of the extremely good finishes and huge amount of repetition. This almost takes about 150 to 200 repetitions. So the very repetition will give the reduce the employee. And added to this, these are the all aluminium formwork. Once you are reached the 150 to 200 repetitions, even if you want to throw it and then as a waste, 85% of that is still retrievable and recyclable and recyclable. So with that concept into consideration, you can actually compare which the embodied carbon and embodied energy. This gives you, in conventional method, from the energy, embodied energy and embodied perspective, 3213 is the conventional embodied energy. For plywood with it is so, and for aluminium formwork it is so much. From embodied carbon perspective, what you see the red graph here, that is so. And then now it is very easy for us to understand that, look, for my project, if it is formwork of aluminium, is most economic, is most sustainable. But does it work, is the another next question. So that is why I said it is always the discretion of the engineer, which should I use. If I have only one building or two building or only one infrastructure project, that repetitions may not use, so then aluminium formwork doesn't become viable. So I can go in for the next possible uh, portion. So that this is how sustainable formwork can be done. There is another method of, it is called figure of merit, which actually is slightly more complicated. It takes into consideration modulus of elasticity, material density, cost of construction, cost of material. Now we saw the embodied energy. How do we calculate from the embodied energy perspective? How do we calculate from the embodied carbon perspective? And now this is what is called as the, how do we calculate from the figure of merit. So figure of merit is a slightly a complicated thing. Let us have some other exclusive session on that. But please know that it is, this is the formula which is used for calculating the figure of merit. And this also, using the figure of merit, we can actually identify and classify the materials. For example, from the figure of merit perspective, we can actually draw the materials in which range it will fall, whether it falls in the low range, whether it falls in the high range, or what exactly is the, where does it fall. So we can figure of merit, and then metals in construction, if we draw from the embodied energy perspective and also from the embodied carbon perspective, we can classify the materials using the figure of merit. Due to paucity of time, I will not be able to explain you in detail. So ultimately, the quadrant based on the figure of merit, we can actually classify all the materials that go into consideration. So for example, if you see here, in this, from the embodied energy perspective and the figure of merit perspective, all these materials, cement mortar, clay brick, granite, glass, marble, sandstone, all these things actually fall in the most suited materials from the sustainability point of view. Then in quadrant 2, if these some materials fall in the quadrant 2. Quadrant 4, which are not sustainable at all, some material, for example, brass, it falls in the non-sustainable material. So it is better not to use brass in the building structure at all. So stainless steel, for example, is another material. Stainless steel, not mild steel. Stainless steel is another material which actually falls in the non-sustainable range. So this is how we actually. So there is one more complicated system of analysis which is called SDI, that is Sustainability Development Index method. This is the most all complicated algorithms, software which is available in the market. They will take this into consideration. And this is actually, I'm happy to share that this actually is my contribution to the field of sustainability. Now, this Sustainability Development Index takes into consideration almost about 28 ecological and engineering parameters, material properties, embedded energies. Embedded energy is embodied energy, and then embodied carbon, feedstock energy, all those energies into consideration. And the benchmark projects, taking everything into consideration. This involves a very complicated algorithms, the mechanical formula. So ultimately, we actually can also calculate it. For same formwork, the way we calculated using embodied energy and then embodied carbon, we used we can use this sustainability development methods. So ultimately, we can per square meter ultimate using sustainability development method, we can also calculate for formwork, conventional formwork, plywood formwork, and the aluminium formwork. This is the, by sustainability development, it gives you a number, a unitless number, based on which you need to assess the parameter. Now this graph literally shows you the complete three systems analysis of the formwork using embedded energy, using embodied carbon, and then using sustainability development index. If you see, in all the cases, aluminium formwork appears to be the most sustainable formwork in the entire sustainability domain. This has to be analyzed. Then the second best is actually the plywood formwork, and then the third one is the conventional formwork. These are actually the figures. If you see the sustainability development figure, if you take 90,000 is for the conventional figure, and aluminium formwork is 30,490. So in this, for the aluminium figure, all figures are completely tell us that it is least impact. So this way, for every system, we actually can use this for the material. Now, this sustainability development index can actually get applied to several methods also. As I said, using this method, we need to establish the benchmark values. And once the benchmark values, as discussed, once we assess this benchmark value, we know what is that we need to achieve. Okay. Now in case of a multi-storied building, let us say the first step, as this particular building in Bangalore is taken as one of the examples, as taken as a embodied energy benchmark project. Now, okay, this benchmark project is a multi-storied building. It has got concrete block work, steel works, block masonry, doors and windows, all these conventional buildings. This embodied energy works to be 3,500, and this also can be actually displayed in the pie chart like this. If you see the pie chart, most complicated contributing factor to the entire embodied energy, embodied carbon, or to the greenhouse gas emission, or to the impact is concrete, and next comes the steel, and next come the formwork. So all other areas actually are literally compared. So if you focus actually on reducing your impact, total impact in concrete, reinforcement, and formwork, and also to a great extent on block work and block masonry, this particular triangle, and if these 4-5 important areas, if we reduce, all the things come into the picture. So this is taken as a benchmark project, and then the analysis was done. The analysis was done. This is the same analysis was done from the embodied energy perspective, from the embodied carbon perspective. Embodied carbon perspective, 316 became the value of the benchmark building, and this also is the pie chart which can be here also from embodied carbon perspective. Also, concrete, steel, formwork, block work become the major areas. All other things have, and these graphs, some of the graphs will tell you very complicated tables, computation tables, but let us not break our heads into this. But eventually, the benchmark values actually can be also from these are the benchmark values from the SDI, from the third method. So once we have established these benchmark values, this has been, as I said, this have to be verified from the green rating systems, only because just to validate what the benchmarking system, what we have done is correct or not. As discussed earlier, the benchmarking project stands in the platinum rating. So our benchmarking project is good and then can be compared as a project. Now, this is the scenario in most of the conventional buildings. This is actually is one of the multi-storied, most posh apartment complex in Bangalore, which is taken. And this is a regular salient features: residential building of 17 floors, RCC frame, 25,000 square meters. Envelope is solid concrete blocks, and then they have used Clyde this thing. Flooring is vitrified tiles, granite, combination of everything, joinery, wood, UPVC, plywood, formwork, conventional. Please understand that they have used the formwork conventional here. Waterproofing, membrane type, climatic reason. So these are the standard specifications what we see. So this is taken as the based on the real-time data. What is the real-time data? That means when the project is on the drawing board, we have calculated the bill of quantities based on the architectural design. Please remember that the project is not yet constructed at all. The project is not conceived. It is the pre-phase construction phase. That is why this becomes more and more important. Now I calculate exactly the same way what I discussed according to the standard areas, the total reinforced concrete, plain concrete, vacuum dewatered floor concrete, reinforcement, etc. These are the various important parameters in that building. And the way now what is the total bill of quantities? These are the what is the taken from the bill of quantities, and ultimately the total area is known to us, and these every individual parameter is reduced to per square meter what is the total quantity, and then it is reduced to, using the density of materials, it is reduced to kgs, or it can be some items are calculated per unit square meter or cubic meter also. Depending, this we have to do it depending on the values we get it in the inventory tables. So ultimately, as we have discussed from the tables, etc., we, from the embodied energy perspective, this 5185 per megajoules per square meter is the value. Correct? Now, similarly, we can, and then we can actually distribute it in the pie chart, taking all these things. So let us not worry about it. Now, similarly, from the embodied carbon per square meters, we can calculate, and this building gives 483 kg CO2e per square meter. How much our benchmark was there? It was 350. So now that means I have, from embodied carbon perspective, in these materials, I also know from this particular area which is the highest embodied carbon, which component, which part is contributing more to the carbon, and that part if we play on, I can make it move towards the benchmark project, that means to try to bring this 483.75 to 350 per square meter value. So this is the same pie chart from it. And now this is the third method from the Sustainability Development Index. We can also draw exactly the same pie chart and then same analysis. And finally, we can actually compare all the projects, all the three projects as we did earlier. Now, this can be done with for the cluster of projects also. So we need to go into details as far as the cluster of projects is concerned. We need to take sustainability standard deviation into consideration, and the variance, then the baseline values, range values. So for everything, similar typology of buildings, these things also can be applied. And once we apply that building, it is possible for us to calculate and classify non-sustainable, least sustainable, moderately sustainable, and highly sustainable building. So from 0% to 100% sustainability models we can actually travel. And once it is done, this from embodied energy perspective, And from all the three perspectives, we can actually understand, draw the mean line, draw the standard variation for the cluster of projects. We can place these projects. For example, in the cluster of projects taken, few of the projects are falling in this range. So that means it is moderately sustainable. Some of this particular project, let us say, project number one of the projects is falling with 5.96 gigajoules per square meter, which is 5,960, which actually falls in the non-sustainable material project. So like this, we can actually classify the buildings with all the values and then perspective. So in conclusion, sustainable assessment leads to us embedded energies, embodied energy, embodied carbon, material suitability, material classification, building classification, building clusters, and all these things actually can be done. So ultimately, when we come to how do we do it, the only way forward is, once we have understood the core issue, core principles of all these design parameters and design principles, decarbonization is one way. In three simple terms, with all the background what we have seen, we need to optimize the energy efficiency. We need to reduce the carbon footprint, that is the impact of embodied carbon. That is this, in the first, energy efficiency is the optimization of the embodied energy, optimization of the embodied carbon, and then the fuel switching. That means use renewable energy to the extent wherever it is possible. That is the fundamental basis. All these things actually we have taken into consideration, talked about it. The key aspects to be addressed, we talked as one of the key parameters in flexibility, and then resilience. Basically, we need resilience in terms of soil, resilience in terms of water, resilience of flexibility in terms of air pollution, etc., resilience in terms of earthquake, and all these things we need to take into consideration. And emerging need for the paradigm shift, which we already talked about it. From pre-disaster mitigation, we need actually to come to post-disaster mitigation. We need to assess the project before it actually takes into the execution stage. So once we know that the building, for example, on the drawing board itself, that this building is not going to be sustainable, we have lots of options to change the technology, to change to change the methodology, to play with the materials, to play with all those things, and then bring the material as to the most sustainable building or infrastructure project. This is as far as the new projects are concerned, or the green projects are concerned. As far as the existing projects are concerned, we need to actually work out with how do we retrofit them, and is it worth retrofitting them or demolishing them. That is a different, altogether a different analysis. And then in 7:16, and now it is 9:18 or 9:17, I have taken 2 hours, half an hour I have left it for your question and answer. Thank you.
Thank you, sir. It was very in detail presentation about the sustainable construction. I request participant, if you have any doubt, queries, you can ask. You can unmute yourself and ask the question, or even you can write it in a chat box.
Hello, sir.
Yeah, can you please read the chat box question?
Yeah, name, sir?
There is no question in the chat box.
No,
There is no question in the chat box.
No, sir, we have got a few questions.
Yeah, please.
Actually, I'm accompanied in this session with my husband, who is a practicing consulting civil engineer.
Yeah.
So he would like to ask some questions, sir. I'll just transfer it to him.
Yeah.
Good evening, sir. It was very nice presentation by you.
Thank you, sir. Thank you so much.
I really enjoyed that. I have a few questions. First thing, sustainability should start from the beginning itself, as you said.
Yes.
My question is regarding the factor of safety what we are adopting.
Hmm.
At the time of investigation of the site, the soil investigation is done, then the factor of safety taken.
If a recycled steel or not recycled steel, whatever it is, when we test it, let us say in a trustworthy laboratory, if the recycled steel or the secondary steel gives me the same properties as the virgin steel, I should not
Yeah.
have any problem in reusing it. Now the clients will have a problem to reuse it. A recycled steel ಬೇಡರಿ ಅಂತ ಹೇಳ್ತಾರೆ. No, it's a
Yes.
question matter of convincing the